Welcome to our last Special Topics videos designed to help students prepare for the organic chemistry sections of their standardized exams. Today we'll be pulling together the last remaining loose ends, fundamental organic reactions and principles that require readdressing but I haven't really given full attention to yet. Now once again, to benefit most highly from this, all those who listen to this lecture should be nearing the end of their second semester of organic chemistry. After this lecture, you should be able to arrange molecules according to acidity and basicity. You should also know the reagents and be able to predict the products of the following reactions: Aldol condensations, Claisen condensations, intramolecular diketone condensations, and Malonic Ester Syntheses. I realize that it may feel I'm regressing to something I already taught you in an earlier Special Topics video, and indeed I am. But I promise you that our return to this topic will ultimately pay off if you give it the proper attention. As I mentioned in an earlier lecture, acidity can really be thought of simply as being a reflection of how easily a proton or an H+ can be removed. I think of this as kind of being like a tug of war. Let's pretend that these three guys over here are pulling on this rope away from this little guy over here. Now these three guys represent the rest of an acidic molecule, and this little guy over here represents an acidic hydrogen who's only holding onto the rope by one hand. See? He's waving at us! Now along comes a big bad base. Because these guys over here in the molecule are pulling the rope away from the hydrogen's grip on the rope is loosened. Thus the base has a much easier time removing the hydrogen from the rope. Hence, this hydrogen's acidity has been increased because the rest of the molecule is pulling away from it. This, of course, results in the formation of this product, in which the rest of the molecule kind of looks a little sad. Now, this is the kind of scenario that we would see in a molecule like this, where these three electronegative fluorines are pulling electron density away from this acidic hydrogen. This loosens the hydrogen's grip on this oxygen and hence on the rest of the molecule, so to speak, making it easier to remove by a base and hence more acidic. Now if we imagine an alternative scenario in which the rest of the molecule is made up of guys like these, who are really lazy and aren't even pulling on the rope, we can see that the hydrogen's grip over here is not loosened as much. As a result, the base has to work much harder to be able to remove this hydrogen. Thus, the hydrogen is much less acidic. This scenario can be compared with a molecule like this, where there are no electronegative withdrawing groups like the fluorines in the previous example to pull electron density away from this hydrogen. Because this hydrogen's grip hasn't been loosed on the molecule quite as much as it was in the previous example, this hydrogen is not as acidic. Thus, the base has a harder time removing it than it did in the example on the previous slide. Now we contrast that with an example like this, where these guys are actually pushing the rope toward the hydrogen. Now I realize that this would be slightly ridiculous in a real-life tug-of-war, but I hope you can imagine hypothetically that this actually tightens the hydrogen's grip on the rope and makes it much more difficult for a base to come and remove it. This scenario is kind of like one that we'd see in which there's a molecule like this electron donating group pushing via resonance electron density toward this hydrogen. This effectively tightens the hydrogen's grip on the molecule, making it much less acidic. Because the hydrogen's grip hasn't been loosed as much, the hydrogen isn't as acidic as it would be if I had just a hydrogen here instead of this donating group or a withdrawing group. So remember then, withdrawing groups increase acidity and donating groups decrease acidity. We saw this principle applied earlier to these molecules, for which I asked you guys to explain how you thought the added halogen atoms would affect the acidities of the encircled hydrogens relative to acetic acid, shown right here. I also asked you to earlier apply this principle to these questions, which I won't readdress here. You may remember from our very first organic chemistry lecture this year that I taught you about pKa values. Now at that time you'll recall my teaching you that the lower the pKa value, the more acidic the hydrogen is. Now here are some pKa values that you really should memorize. First one, a hydrogen stuck to an alpha carbon, that is a carbon that's alpha to a carbonyl, has a pKa of around 20. A hydrogen that's on a fully alkylated or protonated nitrogen, this is an ammonium hydrogen, has a pKa of about 10. Similarly, a hydrogen on a phenol has a pKa of about 10. A hydrogen on a carboxylic acid has a pKa of about 5. A hydrogen on a protonated alcohol, such as a hydronium ion or a protonated ether, has a pKa of about -2. And a hydrogen on an alcohol or water has a pKa of around 16. Now, of course, there's going to be a lot of variety in these pKa's for specific examples depending on what groups are attached to them. But generally speaking, these are about the types of pKa's that you would see for these types of hydrogens. Now, you might ask, why do these hydrogens have the relative stabilities that they do? The answer is because of the relative stabilities of their conjugate bases. And you should always remember, the more acidic the compound, the less basic will be its conjugate base, and vice versa. Now that we've reviewed acidity, I want to apply similar logic to help us predict and sort molecules according to their basicities, which property behaves in an analogous but opposite fashion. Simply defined, basicity is a measure of how easily electrons can come out of a compound to steal a proton. So if we imagine this E- here as being a set of basic lone pair electrons wanting to steal this proton right here, then we can further envision it being attached to the rest of a tug-of-war molecule shown here. You should be able to see that the trend for basicity is opposite that of acidity, because these three guys right here are pulling the rope away from these electrons. The electron's ability to come and grab this hydrogen has been decreased. Thus, because these electrons are much less available, the molecule is less basic. We can liken this to the scenario in which we see a molecule like this, where basic electrons, these negatively charged electrons here on this oxygen, are being sucked by resonance into this group over here, this electron withdrawing nitro group on the ring. Now, because this withdrawing group makes the electrons much less available here on this oxygen, this molecule is much less basic than its counterpart that would lack the nitro group. Thus, we can see that withdrawing groups decrease basicity because they make electrons less available. In contrast, if our basic electrons were instead at the end of a rope in which the rest of the molecule was pushing toward them, then it would make them much more reactive and readily available for grabbing protons, that is, more basic. This type of scenario is the one that we would see in this kind of molecule, where an electron donating group, this methoxy group, is actually pushing via resonance electron density toward this negatively charged oxygen. Thus, we can conclude that donating groups increase basicity because they make basic electrons much more available. So this negatively charged oxygen would be much more basic than the one on the previous slide. To conclude then, basic electrons that are tied up by electron withdrawing groups or by resonance or by any other factor that makes them less reactive and less available will be less basic. In contrast, basic electrons that are juiced up or are made more available by electron donating groups that push electron density toward them will be more reactive and hence more basic. This same logic also applies analogously to nucleophiles. So let's examine some sample questions that address these acidity-basicity principles. I want you to sort the following according to their relative acidities from most to least acidic. I want you to sort the following according to their relative basicities from most to least basic. Which of the following would be the strongest acid and why? Which of the following would be the stronger base and why? Sort the following according to their relative basicities, from most to least basic. Sort the following according to their nucleophilicity, from most to least nucleophilic. And which of the following is the most acidic? Why? We'll now move on to reviewing some fundamentally cool reactions that repeatedly pop up on standardized exams. The first is this one, called the Aldol reaction. If I take an aldehyde like this and treat it with base, just hydroxide simply, that base will remove an alpha hydrogen, and the negative charge on that alpha hydrogen can condense and attack another molecule of aldehyde, ultimately arriving at this product. Similarly, if I do the same thing to a ketone, an analogous thing occurs to give me this product. The products are beta-hydroxyaldehydes or beta-hydroxyketones, respectively. Now, I hasten to mention that the Aldol reaction is only possible because alpha hydrogens are somewhat acidic. They have a pKa of around 20 due to the resonance that they have into the adjacent carbonyl oxygen. Thus, when you remove an alpha hydrogen, the resulting negative charge is resonance stabilized into the carbonyl oxygen. When you have a negative charge in a conjugate base that is stabilized, it makes the resulting conjugate acid more acidic. Here's the overall reaction's mechanism. I have my aldehyde right here. My base comes and removes this alpha hydrogen, dumping these electrons in here. Now, you might ask the question then, why is this so acidic? The reason is because this negative charge resonates into this carbonyl oxygen by resonance. At this stage, this negative charge will then come and attack a second molecule of starting material aldehyde, pushing these electrons up onto the oxygen. That gives me this intermediate. Now, this might be kind of difficult to see how you get from this to this, but keep in mind I'm putting two of these molecules together. And you can, of course, look at this numerous times until this makes sense. At this stage, this molecule then will grab a proton from water in the solvent to ultimately arrive at this product. Now, typically, these products are not drawn in this fashion. They're drawn in a more straight-chain, sawtooth way, which is sometimes difficult to see immediately. So I've tried to facilitate or make that a little bit easier to see by numbering the carbons around this skeleton structure. You can see carbon 1, 2, 3, and 4. I can redraw this molecule as being this, and you can see, just as I showed in the previous slide, that it is indeed a beta-hydroxyaldehyde. Another perpetually addressed and very useful reaction that you'll see on standardized exams is this one, called the Claisen condensation. The Claisen condensation is very similar to the Aldol reaction, except that it involves two esters instead of two aldehydes or ketones. By analogy, the product looks very similar to an aldol product, except that it has a beta-keto ester instead of a beta-hydroxyaldehyde. So basically what occurs here is we have to have a base that matches the ester. So you see I've got an ethoxide here that matches the ethoxy group on the ester. It will then deprotonate the alpha hydrogen. That alpha hydrogen comes in and condenses on a second molecule of the same ester, and ultimately kicks off the ethoxide group to give me this final product. Now, you might be looking at this and thinking, what in the world does that mean? Let's take a look at the reaction mechanism. Here it is. I have my starting material ester. I treat it with a base, and once again this alkoxide base has to match the ester, or else I'll just get transesterification occurring competitively. The alkoxide base removes this alpha hydrogen to give me this enolate. This negatively charged carbon then comes in and attacks a carbonyl from a second molecule of starting material ester. The electrons go up, and it gives me this intermediate. Now, this is a little bit different from the aldol reaction because an aldol reaction has a hydrogen here or an alkyl group here, which is not a good leaving group. In contrast, an ester group has an OR, which is a comparatively good leaving group. Thus, at this stage, these electrons come down and kick off the leaving group, ultimately providing this product. Now, if you look at this closely, you will see that it is indeed a beta-keto ester product. This might not be as easy to see, however, until we look at the numbers. Carbon 1, 2, 3, and 4. I redraw that, you can see that it is indeed this molecule, which is an ester that has a ketone at the position beta relative to the carbonyl. It is a beta ketoester. I hope you feel comfortable with this, because we're going to do some problems. First, I want you to identify the aldol products formed by reacting the following molecules with sodium hydroxide. Next, I want you to identify the products of the following Claisen condensation reactions. And next, I want you to identify the missing starting materials in each of the following Claisen condensation reactions. The comparative acidity of alpha hydrogens in carbonyl compounds enables their deprotonation and reactivity to be achieved with relative ease. Thus, if I take a diester of this type and treat it with a base, and once again you'll see that the base has to match the ester, then alpha deprotonation will occur. The resulting negative charge here on this alpha carbon can then cyclize on to the other ester carbonyl. You can see that the electrons then go up, and then the electrons go down to kick off this methoxy group, ultimately providing me this. You can see that by condensing onto another ester inside a molecule, this is an intramolecular condensation, I ultimately end up with a cyclic product as shown here. This reaction is called the Diketone condensation. Similarly, if I react a diketone, such as this 1,4-diketone with base, external deprotonation of this alpha hydrogen will give me this intermediate. When this negatively charged carbon comes in and cyclizes on this carbonyl to push these electrons up, it then gives me this intermediate. Now this negative charge then will linger until we quench it, and upon protonation it will give me this final beta hydroxyketone product. Now you may be wondering, for this starting material, why we didn't remove alpha hydrogens from this carbon instead of the ones from the external carbon. That is a good question. Let's look at that now. You can imagine that if I removed the alpha hydrogens here, I would get this enolate. Looks fine to me, right? Now imagine that if this negatively charged carbon closed in at this carbonyl to form a bond, what would the ring size be? It would form a 3-membered ring, and ultimately upon protonation, this 3-membered ringed beta hydroxyketone. I want you to understand that this product is much, much less stable and less favored than the product up here. Why? Because a 3-membered ring has serious angle strain relative to a 5-membered ring. Thus, we learn from this example that 5- and 6-membered rings are the most stable and hence the most favored. Other sized rings will generally not be formed in significant amounts unless there are no other options available. So let's look at this example. Here I have a 1,6-diketone. I could deprotonate from the external carbon, giving me this enolate. And if this enolate condenses on the carbonyl, I end up with a 7-membered ring, and this product after protonation. In contrast, if I deprotonate at the internal alpha carbon and then condense onto the carbonyl, I end up with this 5-membered ring, ultimately giving me this product after protonation. Which of these two products is favored? You're absolutely right. It's the bottom one, actually, and the reason is because I form a 5-membered ring, which is much more stable than a 7-membered ring. One additional thing that you should note is that these diketone products can be subsequently dehydrated to give alpha-beta unsaturated ketones. For example, a 1,5-diketone starting material like this, upon treatment with base, would eventually give this product right here. Now, if this product were treated with base, in other words, if I continue stirring it with hydroxide or acid and heat, I will get a dehydration E2 product, giving me this product, which is indeed an alpha-beta unsaturated ketone. Isn't that cool? I think so. In fact, if it doesn't make you cry with wonder and amazement, then you must be a heartless monster. Yeah, okay, it isn't quite that amazing, but it is a whole heck of a lot cooler than tasting deodorant, which I have done. it made my mouth very dry. Now similarly, if we treat a 1,7 diketone, like this one shown here with base, I end up with a 6-membered ring here, which would result from deprotonation of this alpha carbon and then eventual closure onto this carbonyl. If I continue stirring that with base or acid, I get dehydration, which results in this product, another alpha-beta unsaturated product. Got it? Good. Let's go to some questions. What are the products of the following diketone condensations? Why are the observed ring sizes formed in the product? Related chemistry can also be applied to starting materials that look like this. A Malonic ester. A malonic ester. Thus, if we react a malonic ester like this diethyl malonate with a matching base and an alkyl halide, and then I eventually quench with acid and heat, I can get this product, which is a carboxylic acid in which the alpha carbon here has been extended by the alkyl group chain attached to this alkyl halide. This reaction sequence is called a Malonic Ester Synthesis. So what in the world am I talking about? Well, here's the mechanism. I take my malonic ester and I treat it with a matching base, and that base deprotonates the alpha hydrogen to give me this negatively charged enolate intermediate. I then react this with an alkyl halide of whatever type I want, and this negative charge on the carbon attacks the alkyl group to kick off the bromide, giving me an alpha alkylated intermediate. At this stage, I then heat it up, and I will get hydrolysis of both of these ester groups to give me OHs here instead of ORs. That's achieved by the water going in, electrons go up, electrons go down, and eventually kick off protonated OR, replacing the ORs with OHs. At this point, continued heat then allows the water to come in here, thrust these electrons in here, and push them up onto this position. You'll notice that when these electrons get thrust in here, it forms this molecule, which is CO2, carbon dioxide. The negative charge at this alpha carbon then gets protonated in the workup to ultimately give me my final product. This reaction right here is decarboxylation, which we highlighted earlier. Expressed in net form, the malonic ester synthesis looks like this. I take my malonic ester, treat it with a matching base, alkyl halide, and acid and heat, and I ultimately get this carboxylic acid product. And believe it or not, malonic esters can also be dialkylated as well. Allow me to explain. I can take my malonic ester, treat it with a matching base and alkyl halide, followed by a second matching base and alkyl halide, and get a dialkylated intermediate. Upon treatment with aqueous acid and heat, I then do decarboxylation to ultimately arrive at this product. Now that we've taught you that, let's take a look at some actual problems. How could you prepare each of the following molecules using a malonic ester synthesis? And now, my dear students, that takes us to the end of our special topics lecture videos. It's been a long and intense semester, I know, but I hope you've learned a lot from this class. I know that I have. I got to tell you guys, it's been wonderful to be your teacher. Although it sounds cheesy to say this, I really believe that I will remember every single one of you students for the rest of my life, my sweet organic chemistry students. So until later, I hope you guys have a good day.